We were discussing the different ways in which two lines can lie on a plane. In the first pair of linear equations we saw, the lines intersected at one point. Consistent pair of equations. In the second pair of equations, the two lines were parallel. No solution, an inconsistent pair of linear equations. Is there any other way in which two lines can lie on a plane? So let me give you two more equations. X minus 2y equals 3 and 2x minus 4y equals 6. Now try making the coordinate tables for each of these equations. For 3 random values of x, these are the coordinates we get. 3 coordinates for the first equation and 3 for the second. We will plot the coordinates of the first equation in red. We have these 3 points, and we draw a red line passing through them. This line represents the first equation. Now we plot the 3 coordinates of the second equation in blue. Wait, did you see that? These points lie on the same line which represents the first equation. So the blue line of the second equation will coincide with the line of the first. Amazing, isn't it? This was the third way in which two lines can lie on a plane. They can coincide. They are called coincident lines. Wait, how many solutions do you think this pair of linear equations will have? Look at it logically. All the points that lie on both the lines will be the solutions to this pair of linear equations. As the lines are coincident, all the points of one line will also lie on the other. And as a line has infinite points, this pair of linear equations will also have infinite solutions. And what is this kind of pair of equations called? It's called a dependent pair of linear equations in two variables. It's also consistent as it has solutions, but this special case is called as dependent pair of linear equations. Now that we've seen the 3 types, let's summarize them in a very interesting way. Do you remember the general form of pair of linear equations in two variables? The first equation is a1x plus b1y plus c1 equals 0. And the second one can be written as a2x plus b2y plus c2 equals 0. On this note, let's write the 3 pairs of equations we'd seen in our videos. We've written the equations keeping the general form in mind. In the first column of our table, we have written the 3 pairs of equations. In the first pair, the lines intersected and they had exactly one solution. In the second pair, the lines were parallel and they had no solutions. In the third pair, the lines were coincident and they had infinite solutions. Yes, I have a small exercise for you. I want you to find the values of a1 over a2, b1 over b2 and c1 over c2 for each of the pairs. Let me do the first one for you. a1 and a2 are both 1. Hence, a1 over a2 will equal 1 over 1, which is 1. b1 is 1 and b2 is negative 1. Hence, b1 over b2 is 1 over negative 1, which equals negative 1. And c1 is negative 4 and c2 is negative 2. Negative 4 over negative 2 is 2. In a similar way, I want you to find out these 3 ratios for each pair. These are the ratios you should have got. Now in each case individually, I want you to compare the ratios. In the first case, we can see that a1 over a2 is not equal to b1 over b2. While in the second and the third cases, a1 over a2 is equal to b1 over b2. Actually, in the third case, all 3 ratios are equal. And in the second, these two are not equal to c1 over c2. The 3 types are consistent, inconsistent, and dependent. So this table summarizes pretty much what you need to know about pairs of linear equations in two variables. When these 2 ratios are not equal, the lines intersect. When these two ratios are equal but not equal to C1 over C2, then the lines are parallel. When these two ratios are equal to C1 over C2, then the lines are coincident. Review this table again and your concepts about graphing pairs of linear equations in two variables will be crystal clear.